Hello, good morning everybody, and welcome to lecture 12, which is a set of two. Actually, it's lecture 12 and 13 tomorrow deal with MEP and active systems. You remember last week we dealt with interior environment in terms of passive systems, those which we can use without need of energy, just based on our intelligent planning and design of the building. But in most climates, there are moments in which we need additional systems to improve the level of comfort or safety in some cases. And that's when we use the active systems, those that use electricity. Those two lectures will end all the technical contents of the course, so please hold with me those two sessions. And well, I know MEP is not a popular subject, and most people don't like it because it is very much in the realm of engineers, and it's quite wide, complex, but it's not as complex in reality, in the principles, not in the details of calculating and detailing. And some of them really affect the final result of the building in terms of the space usage and in terms of the space configuration. So it's not bad idea you have at least a basic understanding, so you have an expectation of how much those systems may affect your design, how much they can help to provide a better or more adequate environment, and also for you to be able to arrange things in a way that engineers do not have to struggle, and that you can communicate with them better because you will understand and you will know what you are speaking about. So let's go into it. Before we go into the lecture, we have to speak of the assignment in which you will develop or you will try to study the basic systems in your own project. So I gave numbers correlative. So this week you submitted assignment 3, which was just the basic information of your project. And assignment 4, which is next week, will deal with the structure, which is a system we already studied. And we will explain a little bit more in detail tomorrow, which we have a lecture, which is a bit shorter. And yes, I will have time to also show some samples. Following week, we developed the envelope, which is a facade and roof. And probably this is the part which affects most the design, and in which most architects put some effort, because really that's part of your detailing. But it's not only design, it is also the first barrier against the exterior, or regulating how inside and outside relate. So this is the first part which will define actually how a building will perform related to climate. Then in the following week, we will have a basic assignment of MEP planning. It will be mostly diagrams. Right. But for us to be aware on how those systems can be implemented in the building, and even though they might be cumbersome or large, they can be integrated in the general concept of design. And finally, I think important, it's about green strategies and integration. Integration is nothing more than putting all together. Right, so we have structure, we have envelope, we have systems, we have green strategies, and this is all part of the same project. So we put it all together, and then after that, we have a bit more than 2 weeks, actually it's 2 weeks and 2 days, to complete the final assignment, which is assignments 4 to 7, all those clean and corrected. I will check your assignments one by one, the whole class, week by week, and give feedback in things you can correct or you should correct and you can improve. And with that feedback, you will create a clean final assignment that you will collect in one booklet. We will comment more in detail on its time, right? So clean and corrected. And of course, this is your probably your first experience in integrating your own design with all the technicalities you learned through the years, and we are reviewing it now in our course. It will be the last day of class instead of the final exam, but since you have your own calendar and you have a design studio and other courses and I don't know, whatever, I will give you the opportunity to submit like 5 days before, so you can get liberated from it, and well, that will be your final submission. For structure, you have the basic requirements, which is no more than one A3 sheet, which I think is minimum to describe a basic diagram and a few details. And of course, if you want to do more, I will limit it so you summarize and you don't overwork to one A1 or 4 A3, which is the same. And I think it's more than enough to have a basic idea description on how your project works in terms of structure. What should you do? First, and this is something you should do in all projects, is a plan structure diagram, floor plan structure diagram. And depending on the size of your project, 1 to 200 should be the minimum, but if the project is large, you can go to 1 to 500. And there you describe only structure. We'll comment more tomorrow with some examples, but this is only structure. Columns, walls, beams, slabs, etc. With dimensions and spans. Because you know, design in architecture has a lot to do with dimensions, sizes, and the proportions of the spaces for many reasons. Then, very important, and this is something that engineers do not do as much as they should, is section diagrams. Again, well, 1 to 300, or 1 to 100. Usually in section, you need a bit more height to understand the floors, otherwise things become too small. This is why I advise to enlarge the scale to see how the vertical elements relate and the position of the horizontal elements with the openings, the stairs, and so on. And in that section, it will be interesting you pre-dimension the beams and slabs to know how much height that the structure needs, right? So your section and your project afterwards will have a realistic, or at least a reasonable set of dimensions. And you may have to correct heights. Of course, you have to give also dimensions of heights, labels of floors and so on, but we will comment on that tomorrow. And then you can add, I recommend, you should, but the basic are 1 and 2, foundations, again with pre-dimensions, and we gave in the lecture and the additional materials some tips about it and some details. Right? And that should be at least 1 to 50 for you to consider joints or specific points that you think might be interesting. In Blackboard, you have a checklist for all the assignments, which I think is a nice document. You know, we have samples of students, we have project samples, and we'll try to complete the collection as we need. And you have the materials in the lectures and other references. So there's plenty of material to look around. You don't need to go, well, you can go, of course, but you need to go to make a neighbor or Google search to try to find the detail you need and just copy without knowing what you're doing. So if we have the whole course and all that super material, is for you to have at least that basic understanding. And as I told, in Blackboard, you have the checklists. It is outdated to this year, so I added some comments and reorganized a little bit the content, and also took into account that this semester we are working mainly online. So please go to Blackboard, download it, and you have a general tips for presentation, which is just 6 points. Please follow them. There are things as elementary as putting your name Of course, you do not staple because we are doing online, right? But put in title box in your drawings or title area and put it always in the same place of drawings, not having title one drawing on the bottom or the on the top, or the rotated. So try to make your drawings a little bit more professionally. Then, very important, you have a set of 10 points, which is the, if you never read, please at least follow the basics. This is something that is very much common sense, but will help you understand much better how technical drawing sets are organized, and will give you some kind of guidance or discipline on how to do things in a way which is organized, not very random or disorganized, which is something which happens often because probably nobody taught you about it. Then you will have chapters of tips regarding each of the assignments. So you have already, after the general, you have some other tips in general detailing and material schedules. And then you have a structure, you have an envelope, and you have MEP and green and so on. Please refer to it, and I hope this helps. So let's go into the lecture because time is running. And the whole set of 2 lectures will deal with all systems. Today, we will concentrate on artificial light, which complements what we saw yesterday about natural light, and mechanical systems, ventilation and heating, which is quite cumbersome, and it's one of the most annoying in architecture. As you say in the photo, this is a modern building in coex, right? And more than half the roof is filled with those kind of cooling, heating machines, and then of course communication and the other systems. This is very well done, quite intelligently, because the systems are well hidden in the top, so the sound is trapped and doesn't disturb much. But well, nonetheless, mechanical systems take a lot of space and a lot of work to organize. And then the following lecture tomorrow, we will deal with a bit less annoying systems, plumbing, which is important and deals with water, especially sewage. We have to consider electrical, conveyance, and safety, which is not really one MEP system, but is connected because you need electricity and need plumbing also. But we are dealing more on the sense of safety by itself, especially in terms of design and passive egress or escape system for inhabitants. With this, let's go into the lecture, and just remind you own material. Edward Allen, the studio companion, gives you pretty much tips for almost every technical element you need in a project. And I selected some excerpts with the practical information you can use to dimension and to plan your MEP systems in the project in terms of rough pre-dimensioning for design before you send things to an engineer, and also for safety and escape. So please refer to Blackboard if you need more than you see in the lectures. Right, so cooling, heating, MEP, and egress are the elements which you have. And if you want more, you can go to the book, and you will have from structure to almost anything you need to decide in terms of dimensions in your project. Let's start with artificial light, which is a great invention. And since we have a lot of nocturnal life, we need that. And thanks to electricity, we have a wide range of possibilities of light in these spaces. So we need, if you go to artificial light, we need to understand some of the basics. And the first one is of color. If we see the whole radiation spectrum, the visible light is a really, really tiny part of that spectrum, like a little less than 400 nanometers for very short waves, which is ultraviolet, to a little more than 700 nanometers, which we go to the infrared. You know that ultraviolet is important for our life, so it's part of our biological processes need ultraviolet, but in excess and it's very easy to reach the excess, creates biological damage. And the more you go, of course, X-rays, gamma rays are those used in, well, this is the radioactivity produced rays, so they really have a biological damage, and this is rays you have to be a minimum exposure to. And infrared are not as dangerous as ultraviolet, but they produce heat. So they also burn, and burning is not something nice, so it also creates damage for other reasons. And in between, you have all the visible, right? Which is the known, we summarize as 7 colors, right? And they go from violet to red, of course. And the mix of all those colors we perceive as white, as daylight. If we make the spectrum of the artificial light, or the natural light, sorry, we see that sunlight is this red graph. It's a bit irregular, but it has a very nice distribution, right, along the whole spectrum. And although it has peaks, it's quite well organized, with most of the range in the area between green and range of red. But you have a large amount of the blue and so on, and a large amount of red also. And you see it is wider than what we see. This is why sunshine has a lot of ultraviolet, but also infrared. So this is why we have to limit our exposure to sunshine. But what interests now us is that it's very well balanced curve, and that gives us that's the natural perception for which our eyes are designed. We see halogen light, which is maybe one of the best or most natural light we can still afford, because you know the old light bulbs are getting phased out and not sold anymore in many countries. The way they produce the light is not very different from sunshine. So we have this kind of a graph which is very similar to natural light, but it's only shifted towards the red. Right? So what is the advantage? It is quite natural, so it's very smooth spectrum of radiation, but it produces a lot of heat. So that means they become hot and you waste energy, because that's electricity which doesn't produce light. So that's an inconvenience, right? This is heat loss. So this is negative, but it has almost no ultraviolet radiation. So it's positive. You don't have that danger with sunshine, direct sunshine produces in our body. So the other positive element was that the smooth, natural spectrum, right? So it's positive, but shifted toward the red, so it is not so natural as natural light. If we put mercury, which is the white light we see in the streets often, we have just a series of peaks. And since they are mixed of blue, green, red, and so on, we see them as a whitish, but it's a very unnatural white. And this is why when we are at night time under street lights, it's very hard really to distinguish the colors. And they are very efficient because there's not energy loss, but they have ultraviolet radiation, not much, but they have that radiation. This is why they are far away and we do not get sunbathing under street lights. And of course, it has very poor color rendition, so we cannot see. So, you know, to understand how artificial light works, we need to compare with natural light, and that helps us understand a lot their advantages and inconveniences. Let's compare 3 of the most common lights, which is the fluorescent light, the one we have in most classrooms and spaces in public buildings and even in the houses. Incandescent, which is the light bulb, which is disappearing, but it's still interesting to consider. And then halogen, which is the one we commented. Right? So if we put halogen in green, remember we have a very nice, smooth curve, but very much shifted towards the red and with a great amount of heat loss, but very nice amount of energy. If you have the traditional light bulb, the curve is a bit more shifted toward the red, so it's less whitish. And again, in proportion, has a lot of heat loss, even more than halogen. So halogen is not a huge beta, but it's significantly more efficient than incandescent. What happens with the fluorescent light? Let's use the blue. Well, very much as the mercury lamps we saw in the previous slide, it's made by spikes. So just by the mix of the concentration of several colors, you'll have kind of mimicking of white daylight. And you see they're quite well divided. So the feeling is really, in modern fluorescent lights, they sell it as the daylight because it mimics very well. And they have the advantage of not infrared, so there's not heat loss, but there's also no ultraviolet. So it's great advantages, right? So it is very energy efficient, much more than bulbs, much more than halogen, but of course this is not very natural, as there are parts of the spectrum that are lost. And even though we cannot say perfectly, but we recognize always fluorescent light is not great, it's not so natural. If we put LED, it changes a lot. So in LED we can control, and the same as the fluorescent, we have almost no ultraviolet and no infrared, so they're very efficient. But in terms of spectrum, they're a bit more continuous than, let's use the black as in the black. So in terms of spectrum, they're a bit better than fluorescent because it's more divided, so it's a better mix. But there's a big spike on the blue area, right? And then there's a smooth part of the rest of the colors. So you have a really very white, but in general very cold white, and also not great color, let's say, rendition, right? So these are advantages, of course, and this is just in between. It's not terrible, but it's not great, right? So problem is the color rendering, which, and the technology improves, of course, and there's many years already using LED, but yet the achievement of the different colors is better mixing LED of red or yellow or green to achieve additional shades, and probably it improves, but this is one of the missing points. And I bring one example, which is a museum quality LED. You will see in catalogs that sell you LED with a great color rendition index. That means that they show the colors as good as they like. I would suspect, because in 2013, Louvre Museum wanted to change the lighting of Gioconda, because up till that time it was used with halogen light. And of course, halogen light damages the colors because it is organic matter, and the infrared, year after year, makes the painter worse and worse, even though you have plenty of filters to make only white light. So they decided it was the time to change to LED. And what happened? They needed to mix no less than 34 different lamps to have the perfect spectrum with a set of filters. Right? So the light is almost perfect rendition without all those problems of infrared and ultraviolet. You can guess this was not a cheap lamp, but fortunately, that technology may eventually jump into more general use consumer product. I don't know how long it may take, but the technology exists, and this was 7 years ago, or 6-7 years ago, so probably with time we will have access to it. But right now, in the plain consumer LED, especially the cheap ones you can buy around there, suspect when they tell you they have a very high quality in terms of color rendition. So with that introduction, when we design with artificial light, we have a qualitative aspects, things related to the quality of light, and then quantitative aspects. Let's go to the qualities first. And then first is about the feeling of colder or warmer light. And the second, which we commented first, is the precision on color rendering. How accurate is the perception of the colors when we see in light? Let's go to the first, which is what we measure by color temperature. And the second, we measure it by terms of the CRI, color rendering index. So they are normalized numbers, which gives us an idea of how those parameters perform in artificial light. To give you an idea, color temperature is measured in Kelvin degrees, and it seems counterintuitive because lower temperature makes more red, more warm light, right? So this lower temperature means warmer color, and higher temperature means a cooler color. And most artificial light is between the 2500 to the 5000 probably, right? It is the range you can buy. Sunshine is the highest, of course, and fire is the warmest color we have. In commercial terms, as we said, you can buy usually between this range. And this, of course, you don't need to memorize. But if you start from if you say from 2700 to 7000, so just in the middle, if you want to say, or what's the middle? Well, if you can say 5000 daylight, which is what we call by white, and this is what they sell as daylight bulbs, is the white we feel as natural, and it's probably the light we have in the classrooms, in the library, and all those spaces. Under 5000, we'll feel it warm. And over that, we'll feel colder, right? This we have 6000, 7000. It is used in places where they need a very specific light. Usually it's hospitals and some computer rooms. This maybe perform better with this kind of light. And this is why hospitals have this kind of natural feeling. So it's not a big deal, and I think it's not a lot of torture to the memory to have the basic values. Then rendering index, of course, 0% will be no color at all, and 100% will be perfect as daylight. We don't go so far in the range. Usually less than 50% is lights used in storage, corridors, in streets, in highways, which we need just to have light to see the silhouettes, the bulks, but not really the colors. In general, we'll try to go, well, they say 70 to 80, but I think 80 is the aim to be as a general use. And this is what we have to have at least in schools, libraries, and places we need it to work. And 80%, it's not perfect, but we will feel quite comfortable with it. So we'll be able to distinguish quite a lot. And remember, our perception, our feeling of perception is logarithmic. So as in the sound, so we need to change it 10 times the intensity of sound to perceive it twice as big. So in terms of perception, 20% is not something which really feel as a big change, right? But 50 to 78 is a big change. Over that is for better. So usually in houses and places where we spend a long time, we try to go higher than 80. That's what they said. Around 80 is the reference. And in museums and so on, you'll try to go more, much more than 90. This is a very unnatural photo for two reasons. First, it is very unique or very strange to see a whole dungeon, whole set of apartments with all apartments lit at the same time. When we calculate the systems, we don't think all lights, the whole set of lights or the whole apartment of all apartments will be lit at the same time. Usually if that happens, the whole system will blow up because we always consider there will be a percentage of lights which are not used. Otherwise we will over-dimension. And this is a construction site, and they were just checking for that, checking how was the limit of that light supply system. Probably they were not using pumps, elevators, heating, air conditioning, so only light might be okay for the system. But if they had also elevators and heating working on, probably the system would not resist all that load. The other thing is that it's very unusual to have all apartments with the same color. This happens when they put the same quality of light, and this is probably, I wouldn't say, maybe it's already LED daylight or fluorescent daylight bulbs. The most common is this kind of a mixture. So if the following photo comes, we see a mix of colors. So people have more blue, more green, more red, more yellow, depending on the preferences of each. And probably those who are more bluish are people using already LED. And those which are a bit more yellowish are still some kind of warmer fluorescent light in the context of Korea. And of course, you see, you will never see 100% of lights lit, even though this is a very normal hour. It's 10 p.m. and this is normal neighborhood of Seoul. Not even 50% of the lights are on. So we know about the qualities. Let's see about the quantity, and that comes with the intensity, because we need to know how much light is appropriate. And in the case of electricity, you know, more light means more energy used. So we have to be sure we have enough light so people can carry out their activities, but not as much that will just overuse energy, because this is something we do not want to do actually. So intensity is dimensioned usually with lumen. I give also the candela, but in calculations and technical information, you'll have usually the lumen. And candela is just a coefficient, you know, 4p is the sphere area coefficient. So this is kind of another way of dimensioning the light. So more lumen means more light coming out from that kind of emission source, light bulb, fluorescent light, LED, whatever. And with that, we can measure the illuminance, which is usually written as E, in intensity is I. And that's the level of illumination, not what comes out from the bulb, but how much light we have in some point. In terms of classrooms or libraries, it is light on the desk where we measure it. Or in the whiteboard, in the case of a lecture room, right? Because everyone does see it. And this is where we measure the illuminance. So we know the amount of light is correct. And this is measured in lux. And usually is defined as something as simple as 1 lumen per square meter, right? So E can be said as intensity divided by area. We have lux divided by square meter, which is quite reasonable. There's not much mystery here. To give you some basic understanding, 1 lux is more or less the clear full moonlight. So we can see clearly, but actually it's not enough for reading or for distinguishing colors, but still 1 lux is quite some light. And I gave you also the convention factor of candela per square foot to lux. which you can say about 10, or 11 if you want to memorize it with an error by excess of 2%, which is very easy to correct after calculations. And another parameter which is important is the efficacy, right? Which is how many lumen you have, so much intensity regarded to the energy, the power that lamp consumes. And that gives you the efficacy, right? Lumen per watt. LPW means lumen per watt of a lamp. Obviously, an old-fashioned light bulb, not bomb, will have much worse ratio than LED, right? Because maybe what you need with 100 watts in a light bulb, you may need only maybe 15 watts in an LED, and that makes LED so much better efficacy in terms of lighting. But for our lighting project, well, we will try to balance this kind of illuminance and efficacy to make a good project. Just to practice, I give you one example, just to do at home. It is a very basic problem, but based on commercial lights. So I give you the data, and it's kind of displayed like that. And I'm asking you how much you have to separate the lamps, and how much distance you have to provide 500 lux in the lit area. Do you have an idea of how many lamps you need and how much distance they need to be separated from the lit? So if you go very far, you get less light, and if you go very close, you get more light. One parameter you will see in the makers, which we need, is the angle of that light dispersion, right? In this case, it's 51 degrees. I wanted to use a much more easy to calculate angle, but okay, this is what the makers used. With that, you may see the distance and the separation you need, just applying the basic formula. So please work on it, and you see it's not so difficult, and you have some kind of practice to make a rough estimation before using your simulation tools. These are examples of light intensity. As we said, a full moon can go up to 1 lux. And the dark sunlight may be over 30,000 lux to a lot. This is why we shouldn't look at the sunshine. But in general, in buildings, for general use, we will move between 50 to 500 lux. This is more or less this area in which we move in artificial light. Of course, less. So this is for general use, but in areas for just movement and orientation, like streets, corridors, dim light, we go between 50 and, well, nowhere they allow for 1 lux, but probably in emergency lights is between 5 and 10 lux. So you can just find your way and escape. And this is a collection of recommended intensity depending on uses. You see in houses between 500 and 700 is a lot, but you see that the range near part 500. Show windows will need more, of course, but again, 500 is in the middle, right? And also in education, workshops, libraries. So in most places, 500 lux is kind of a decent, intense light for most work. And if you want to go more, you can go up to 1,000. And 1,000 is almost like a surgery rooms or medical examination rooms and so on, right? Of course, restaurants, you may want to be a bit more dim light and so on, but there's not a great deal. And as we said, orientation lights, like emergency lights, something you need to have a lot is between 10 and 50, which gives you that low range, not places you stay, but just move around, and you don't need just to stumble into other people and see more or less the signs for escape. Of course, there are a lot of local regulations. I should follow them. So it is nice to have a tool, to have a basic calculation. Of course, you will use your simulation tools in the computer, but before entering all the data in the program or having all the model in 3 dimensions, you may pretty mention and have a rough idea of how specific space might be lit without spending much work. So what you need is that requires illuminance in lux. This is what we said, what we saw in the slide before. We need to know the area of the room, and the height is important because, you know, we have to know how far the light is from the lit element, and the area to know how many elements we'll need providing light. And then luminaire has a set of lamps, so that's a bit confusing. If you know the lights in the school, you have like a set, maybe 2 to 4 fluorescent tubes, right, in a box. So that box is a luminaire. And each of the bulbs is the lamp. In this case, n is equal 4. So luminaire is the set of lamps plus reflecting. They have mirrors, they have diffusers, they have better light quality, but the intensity is given by the lamps. And this is the n we want to know, right? And the I for each lamp. And with this, we need also the power of watts of each lamp to know how much energy we need, which is not a great mystery. And then the formula is very easy, but we have to add a set of coefficients which are just estimations. One is the utilization, CU, not supermarket, but just a coefficient of utilization that depends very much on height, areas, colors, reflectancy, and so on. And usually the maker will give you an estimation. This is something which reduces the nominal light intensity of the lamps. And other, which also reduces, is the light loss factor. Usually all lamps lose intensity with age. And also as they get older, they accumulate dust and grease and dust from the atmosphere, so they emit less light. And you know, at school, I never saw anybody cleaning the lamps to have better light. But when you clean them, you get surprised on how much brighter the rooms becomes. And in general, we consider 0.7. You see, there's a lot of guesswork in those calculations. And all that data, we just multiply and divide in a formula which is not surprising. If you analyze, it is pretty much common sense. And of course, the power density is the number of luminaires by the watts of each divided by the area. So this gives us a very much useful index, which is how many watts per square meter we install. And that gives us an idea if we are using too much energy or too little energy. And we can change our design, the intensity, or the luminary design, or the lamps themselves, right? So it's a formula, nothing complex on that. And again, just to do once to see how that works. And actually this data is more or less what we have in our classrooms, because I think they're calculated more or less in the 500 lux. So the results will be very much closely related to what we have in class. This you do at home. And if you cannot do, probably your little brother or sister in junior high school, even in elementary school late years, can do the calculation for you. Then with that, we have the basics to make our decisions on artificial light. You know, the color, the mood we need, and also how much light we need. But there are more factors we need to know to make a good lighting project. And this is what we mention now. So there are many things. I just simplified and chose those which I think more important. The unified glare rating, electromagnetic compatibility, that's important because modern lighting has a lot of problems in that sense. And dimmability is about the controls. And there are specific issues to lighting systems. Let's go into them. Glare is something we commented already regarding natural light. So we have too much contrast, especially light going straight into our eyes, we cannot work. So that's uncomfortable. That's what we call glare. And there's a way to measure that. And that comes from both natural light, but also comes from the bulbs hitting at your eyes. So the luminaire design has a lot of effort on putting all the light you need on your desk or wherever you need without hitting your eyes. That is what, to avoid that kind of discomfort. So that is measured with what we call the unified glare rating. And usually, to have an understanding, 5 or less is no glare. That's very good quality. And 40 is like a really, really uncomfortable, really, really something we cannot bear. This is maximum glare. So usually under 10, we say it is acceptable. We don't feel discomfort, but over 30 is unacceptable. We will try to avoid whatever, because we'll feel always the light in our eyes and will be tiring and very unpleasant. And the luminaire makers have to give you this index. So you will choose depending on the uses. This is taken from the United Kingdom standards. And you see that you have less than 16 for technical drawing to almost 30 to just movement places, not really places you work. But you will try whatever be under 20 or under 10. So the less you do, the better, because eyes are sensitive and we need to be in comfort. Then electromagnetic compatibility is a problem that we have with the fluorescent, with LED, and with high intensity discharge. All those mercury or sodium lamps we use in the streets, they have a lot of vibrations, right? And they create interferences with the mobile, Wi-Fi, radio, and so on, and probably in hospitals with a lot of sensitive machines. So in terms of hospitals and high technology places and computer networks, this can be a big problem. And usually the law limits how much radiation any kind of electromagnetic or any kind of electronic device can emit. So we know they will not create any kind of interference which will disrupt networks or other things. And this is a problem with this kind of lights. And fluorescent lamps, right, are more or less controlled, but LED lamps are not so much controlled. They're very new. And this graph is taken from a very wide study. So you have the full essay in the link and also the source of this image. This is one example. And this is a Philips lamp. This is not really a cheap second brand. And these yellow and these red lines are the legal limitations of electromagnetic emission. And you see that even Philips lamps have surpassed that limit on almost all the spectrum, which is unacceptable. And this is very irregular. So same brand may have a very good and very bad lamps in this term. Some of them are really, really under, and there's not problem at all, but many of them are over. And LED is kind of jungle. There's not a real regulation. So most, but not always, most problems are with low voltage LED. You may have problems with high voltage also, but low voltage, you know, we have a 220 volts here in Korea. Japan have 110, but it's a high voltage relatively. Low voltage LED work with 10 volts or 10, 12 volts. So those low voltage may create a lot or less, and we're not sure, I don't know really, if that's because of the device reducing the power or because of LED electronics themselves. And some elements are okay at 10 watts, but then at 12 watts, they produce a lot of vibration and so on. So this is complex, right? But you may suspect more of the low voltage. And I say that because now LED are a hot issue because they save a lot of energy, and many companies are changing the whole building into LED. And they find out that the building suddenly has a lot of interruptions in the Wi-Fi systems, the networks, and that comes from that kind of lack of control on the LED. So careful with that and be aware that that may happen. So careful with this. The other point is fluorescent lights. Fluorescent lights also vibrate, but they have been in the market much longer and we have better control. So usually you will not have that problem. You'll have vibration and humming, especially if they are old, and that's kind of annoying. And this is why you have to replace or find better installation and so on. But in terms of radiation, electromagnetic compatibility is not such a great deal. They have the reactive power consumption, which we'll comment later, but usually it is solved with a ballast. So that's controlled, but you know that if that's not well calibrated and you don't have a ballast there, which is kind of an element which makes sure the electricity that the lamp consumes is only the electricity it needs to produce light, to reduce that kind of reactive power, then you will have overuse of electricity. And this is what the ballast is for. Dimmability is just a way of use. So you know, usually the switch is on or off, all or nothing, but the dimmer allows to have different levels of lighting in the luminaries on the room. The same as you can turn on the power of light in your computer monitor or the volume in your radio, you can do that with light. And not all kinds of lamps can do it. And those who can do it, they have the dimmable label on it. There's many ways to do it. The basic is the potentiometer. So a switch which allows to have more or less electricity into the device. So with less electricity, it has less intensity. With more electricity, it increases the intensity. But thanks to all that advancement in the wireless technology, and even with wires, but there's a lot of control we can do with our mobile phones or home computers. There are two standards, the DALI, which is digital addressable lighting interface, or CASAMBI, which again is going through Bluetooth, that allows the control of light to do an intelligent system. And you will see if those lamps you use will have or will have not that kind of compatibility. So, well, this is what we were commenting before about fluorescent. I think the paragraph is out. LED lamps have an interesting effect, the self-switching on and off with parasite power. What is that? That happens with a low voltage, so low power lamps. You know, we may have one simple LED light working in as little as 5 watts, while a light bulb or a compact fluorescent light will need at least 15 to 20 watts. What happens with this difference? Our usual electricity systems have switches. So this is 0. If we connect it, we have all electricity. When we switch off, we have our circuitry over there. That switch off is not perfect. It's a small amount of current moving around. Alternate power has many interesting things. And one is that there's not 0 in the usual alternate current networks. So there's a very tiny amount of energy, but that's enough for this 5-watt LED to lit on, because you need very little light. And it lights on for a few seconds, it absorbs that energy, and then it switches off. But then current accumulates again, and then it's enough to lit it on, because it needs so little power. And with that light, that disperses the electricity again, and is switched off. And if you don't do anything, it will be on and off until you switch it on again, and it's always on. What is the possibility? One is to have a better switch and more strict network regulation, which is difficult because, you know, this is not a closed circuitry. It is connected to ground. And you have many devices which accumulate power. You have televisions. You have maybe stereo amplifiers which have a lot of condensers. So the electricity keeps moving on the network a little bit. The other way of doing it is to use not simple LED, but luminaires with a set of several. So you have at least 15 to 20 watts. And that's enough for closing that circuitry and not making it work, right? So you have two possibilities. But if you go, especially in small offices, small places like the toilets, corridors, and you change the light, you may have, it doesn't always happen, but you may have your bulbs like lighting on and off like kind of a publicity sign. And we say, okay, reactive power and humming, we commented already. Reactive power is interesting, and you may remember from your high school days when you studied electricity. But well, this happens mainly with the fluorescent and the HDA, high discharge intensity, which we'll comment later, and I give the reference here. One more example. So this is a catalog of a very high quality commercial luminaire. So this is the photo. This is a set of LED with very complex set of mirrors and diffusers to have very good quality light. This is all the fantastic things the dealer is telling us. And you can see what you need. So you know the range of a color temperature they give you from really warm to cold lights. So this is the usual range we can buy. You see that the UGR, the glare ratio, is really low, it's 13.5, which is almost near ideal. You know that's EMC optimized, so it will not create that kind of interference with the electromagnetic waves. Suspect of that also, and if that is the case, be very careful with substitution and changing individual lamps. And you see it's dimmable of all standards with the DALI, with the CASMB, which goes by Bluetooth, or just the usual potentiometer. So you know what to look at when you have a catalog and you see the quality of the luminaire, the possibilities, without relying only on the looks or the price, which, by the way, this is expensive. So again, to do at home, I have a few questions and try to explain and to remember what those three things mean, which we just commented, but not what idea you go back to the lecture and you try to memorize or to at least internalize those things as parameters that you will need to check always. And of course, we cannot go into everything, but I collected a few materials that you can see by yourselves if you want to have more detail. One is ways of using artificial light. This is a section of a room with the element to be lit, the desk, which is the usual, but if you have a, as we said, a lecture room, maybe also the whiteboard or wherever you need the light. So it can be just a spotlight on the working area, spotlight plus indirect light to have an ambient light, only indirect light to have just the basic path, general light, diffuse for the whole room with low intensity, or the whole sets to have a very much regular and the perfect lighting in the whole room, walls, floor, and working place. So it's a very nice summary, and this tells you about how many possibilities you have in a simple space. Then this is kind of all the table, but gives you the basic parameters of color rendition, efficacy, and life, which is also important. We didn't comment about it, but in terms of the economy and sustainability, we need to know how much we can use a given lamp. And among all these sets, the ones we will use more is the halogen, fluorescent, and compact fluorescent. This is a bit old, and there's not yet LED here, because you have all the high pressure, high intensity discharge, which are used mainly on streets, on urbanism, and so on, not inside the buildings, not generally in buildings. And as an example, this is a Seoul night view. So you can see very clearly main street with mercury light. This is my bed, which is white. It's not great, but still it's the best light we have. A much cheaper sodium light, which is this characteristic yellowish, orangish light. It is very cheap, it's low intensity, but it's enough to see the street, to orient and not to stumble into people and so on. But there is no way you can see a color here. Everything is changed. Whereas in mercury, we have a very bad color rendition, but still we're able to distinguish red from green, although we are not able to have much much precision. And those are kinds of light which are very intense and very efficient, or less intense and even more efficient. And then, well, you have a catalog and basic denominations of incandescent lamps, which are less and less used, or fluorescent lamps, which are still very used, and there are a lot of variations, and maybe more than you have in the catalog. The tubes, which are the ones we still have as a standard light in public spaces. The high intensity discharge, the ones we see in streets, but are used also in industry, warehouses, maybe airports and places where you need high intensity, but just a amount of light, not really quality on it. LED, it's crazy because there's so many variations now that we could have a whole monography only on LED. And with that, we go to the other part of the lecture, the mechanical systems, those which has the ventilation, especially air handling. Is annoying because air is, as you see in the photo, takes a lot of space. So we need a very high ceiling space. They are noisy. They are not usually beautiful, so they're ugly. And we cannot ignore them. If we use them, we have to deal with them and see how we can fit in our project. So in general, we call them also HVAC, HVAC, or heating, ventilation, air conditioned, which are all those who use kind of ventilators, fans, and the boilers, and a lot of machines. Maybe this is why they call it mechanical. To understand everything that comes later, I did a diagram which explains which are the elements which we have in most mechanical HVAC systems. Of course, we have first the building, right, in which we have a space that is simplified. This is during summer. So here we are cooling. So we have the fresh, cool air coming in each room. Once it gets hot and dirty, it is collected, kind of return supply, and goes with the exhaust. So we have the fresh air coming in, fresh, cool, and not so fresh, but still cooler than the outside, getting away the building. What happens then? Well, what we do, the best thing we can do is to take this hot air and dirty air exhaust outside to the exterior. And as far as possible, so it doesn't contaminate our people walking on the street, or it's away from the windows, it doesn't come inside the building again, and so on. So you have to make it very far away. In very cheap old systems, a percentage of this exhaust will be recycled. Why? Because in summer this is hot, but still is cooler than the outside. So if you reuse a percentage of it, you're saving energy. But we try to avoid it because we are losing ventilation. And with this world of pandemics, it's a big risk we put air inside, because again, you collect smells, you collect bacteria, you collect viruses, and that goes to the building. So it's a big problem. What we do is using a device which is called heat exchanger. So this exchanger will transfer all the cold still this air has to the new fresh air, which is hot, coming into the building. So when it goes to the fan, it is absorbed, it is pre-cooled in summer or preheated in winter, right? So once it comes to the fan, it will go through a kind of a coil, which has a very, very cold fluid. So this air becomes colder, is filtered, and is supplied again to the building, and the cycle goes there. And of course, this is cooled by a set of two pipes, right? After you cool the air, it's hotter, so it goes to the chiller, the cooler, and it becomes cooled back. So this kind of a circuitry, closed circuit, continuous cooling. And this goes to the chiller, in which you will have two units, so condenser inside and evaporator on the roof usually, or on the exterior. You know, the cooler's always a set of two, and they need a lot of space. In winter, it will be the opposite. We will just have a boiler which is easier, but usually if it is gas or oil or coal, it will produce another exhaust, which we will try to also get out of the building. And the iPod in the outside, this is the heat exchanger principle, which we commented also before. So the air coming in and they're going out do not touch, but they exchange all the heat they have. So in winter, you preheat the air coming in, and in summer you pre-cool it. So you save energy without reusing air, which has, as we said, kind of quite a lot of health issues in that sense. So let's go to systems. Once we know this, there's many ways to put the systems. The most simple is what we call the constant air volume, single duct. This is a very basic section of a building. So we have our fan rooms. So we don't need to explain, this is the coils for heating or cooling. We have the fresh air and exhaust air. It's just one pipe which provides the same amount of air, same amount of temperature to all rooms. And once it is used, it is collected and taken back to the exterior. Let's make it red. It's collected and taken back to the exterior and lost. So this is the cheapest, the simplest, but surely not the best. You know this is a waste. So again, in all systems, you will see part of this air being recycled, which is not something I would advise to do, but you will find it in many buildings, or we can have this kind of exchanger to avoid wasting energy. What is the advantage? It is very simple. Everybody is hot or everybody gets cold. What is the problem? If we have sunshine on one side, those guys are very hot, maybe those guys are very cold. And it is very hard, especially in large buildings, it's very hard to have a comfort everywhere. So that's a big limitation of those systems. The school buildings are mostly this system. The innovation building where I have my office is that system. And I am fortunate, my office is in northeast. Other offices are southwest. And not even in the summer. From early spring, those guys have a really hard time in the afternoon. So they are really, really roasting even in winter because they have so much sunshine in that huge glass area. And of course, the school puts a lot of air condition there, but then myself in the north side, I'm getting cold. So you can see myself having a coat in my room and the guys on the opposite side opening the doors, having fans and almost sweating in the same building and with the same temperature outside. So that's a big inconvenience. To have a bit more control, we have the variable air volume, which is not great, but this is system, but individual control devices in which you can increase or reduce the amount of air. Here, variable air volume. You may have it manually with a thermostat. So in that case, those guys in the west side of innovation building could have a lot of fresh air, but I could lock mine because I'm already cool, and I would be comfortable, right? So this is a big improvement. So it's better, but it's more expensive. Also more complex. That means there are more pieces that can be run, so you need more maintenance, but still not perfect. Because this is everybody cold or everybody hot. You have no choice. You have even much more perfect system, which is multi-zone, in which you have individual ducts per each space. So that gives you the possibility to have a much better control from the beginning. And that modularity also allows for a better use of those chillers, which often are modular, so you may use only one part of it, not the whole power, if only some part of the building needs that kind of energy. And if they are very sophisticated, not the case, but some multi-zone will have some cases, may have also possibility to have hot and cold simultaneously, depending on the needs of the areas, which you see, as I commented, those cases happen. So you may have the possibility to open independently the heating and the cooling per zone. And that's great because that gives you a perfect control of your interior environment. So that happens in some cases, not all. It is perfect, it's very close to that variable system, but it's still even more expensive. And complex because you multiply the number of ducts. So the whole thing becomes a bit more complex, but the system is better. And then we have the just mechanical ventilation with fan coils. This is a very good system because you reduce shafts. So the cold or hot are just by fluid pipes, right? You have ventilation, whatever, so the building is well ventilated. So you have always this kind of renovation of air. So you have full control. And in this case, you may have also all, so you may have a hot or cold as you need, if the system is designed for that. So it's a very good system. It's probably more economical because you reduce a lot of space and you simplify a lot. Those fan coil units are not especially expensive. So you have individual control, right? Even by rooms, which is great. But there's a big but, less energy efficient because they usually have not heat exchange. So all the heat gets lost, and probably may have the exchanger, but with this kind of independent hot and cold use, I don't know how it will work. You could have it, of course, but in this diagram, it doesn't appear. So you may arrange it to have that kind of exchange, but then it will complicate this kind of hot, cold selection you may have. And finally, we have the most simple and also the most individual control also, which we have all by fluids with individual fan coils and not mechanical ventilation, right? Which in terms of simplicity is the best, but then you will rely just on the window opening, which may be not always the best system to save energy. And of course, you have the window units, the single package units, which also you can use, and you have here basic dimensions. And then once we decide the system, we have to decide the position of the fan room, which are huge, and usually we put them on the basement or on the roof on the top floor. But we have cases, depending on the building's intermediate floor, so the shafts are reduced, or fan rooms in each floor, so you have almost no shafts, only individual conductions per floor. There's no perfect system and depends also on the height of the building. So those have a very simple installation, but they have huge shafts, and these other two are intermediate, right? So, and the compromise is not always easy, and something you may decide first based on the character of your project, and then you may discuss with the engineers and probably with the clients also. For the cooling and heating units, it's not the fans, but just the boilers or the coolers, again, can be in the lower part, on the ceiling, or just split nearby. So you have less distance between the interior unit and the exterior unit. And so condenser inside and evaporator outside, I think the set. Because there is also a distance limit. So if you put them very far away, you spend more energy with the pumps and you have a lot of energy loss, which is not very efficient either. You have a basic dimensioning for the split packaged components. So this is what we spoke of this kind of systems here. So those are the split. Let me change this and go here. So this is the split systems. So here you have the basic dimensions and also basic design of a fan room. At the end, you have the tables to have those basic dimensions. Most important is to know that the exhaust air and the income air must be as far away as possible. They say 3 meters, but you can have more. Usually you have the pipes and you make them far away from each other. You have 30 or 100 meters, the more far away they are, the better. Because otherwise you will have always part of this earthy air coming inside and recycled. And you see you will need huge space for those pipes. So depending on the buildings, this can be humongous. And this is when you will make your rough numbers and you will decide if you have a huge humongous duct with enormous fans, you will divide it in smaller pieces. This is the case of a KT building in Gwanghwamun, we say many times. And this building has, that I remember, 1 fan unit per floor. And you see the size of that room. It's not small. And you see the size of those pipes with the isolation. And you see the size of the main duct going to serve just 1 floor. This is enormous, right? So this is something, if you do not consider from the beginning, you have a huge problem reorganizing the spaces and the shafts in your building. Of course, the exterior units, as we saw in the first slide, see how much they take in all buildings. And this is an old building in the lower part, but these are quite recent and actually very good office in them. But see that you want to have a green roof, and the green is less than half the area we have. The rest is all occupied with machines. And this is why we have to be very, very careful to minimize those elements and to organize them well from the beginning. See also how in modern buildings, now in all you need to put screens just to diffuse the sound, because those machines are noisy and they increase the background noise of the city, and they are kind of annoying. So we have always a big problem reducing the noise from so many machines in the buildings. This is an example. This is a Detroit medical center, which is a very much appraised building in I think it's 1970s or early 80s, I'm not sure. It was very modern, and they had a nice move, which said the all mechanical rooms on the middle floor. So we reduce the ducts and we don't have that kind of roof noise coming outside and so on. It was great in theory, but what happens? This floor is kind of resonance box to all those machines. I have a lot of noise going to the street, and on the back going to the other hospital buildings. So a place which is a hospital, which needs a medical center, which is a set of hospitals, which needs silence, is one of the noisiest parts in the whole city. If you go to the backyard, which is a very nicely landscaped area, where the people walk with their hospital gowns and nurses and doctors just have their free time and so on. The sound is like being in an airport with all the noise of the airplanes. So careful with this. And then I collected basic core strategies. We don't need to explain because we commented a lot of things. We commented before in terms of structure. Now you have here advantages and possible disadvantages in terms of those kind of collection of shafts and ducts depending on the system you have, right? And so the strategies, of course, we try to use always the centralized system in small towers, but you see that often other systems have other advantages, and here you have kind of evaluation of which advantages or problems you have in each of those. As an example, again, KT Tower in Gwanghwamun has an outside core. So the office space is almost free of anything else but office space. So we know the position of, we decided the system we use for the mechanical system. We decided the position of the fan rooms. We decided the kind of position of the air handling units, the cores and the shafts. Now we need to have the horizontal ducting, which is simple. In general, we have a main duct, which comes from the fan room. And then you will have individual controls, if that is the system, by rooms or by units, depending on the kind of building you have. And then individual distribution to have that good hot or cold air in each place by means of diffusers. So you try to make them as regular as possible, so you have hot and cold air areas, so it's much more uniform. And also you do them in a way that the air moves to the whole room and is well collected by the return shaft, without having also areas without the air moving. So that's the area which is detailed in this drawing. And this is important in terms of design because that main supply duct takes a lot of the space. They are huge. So the typical is to have that in a corridor, which is great because this is common space. If you need to service, you don't need to access any office, so you don't disturb the tenants or the users. And then the cheapest, fastest is to have that diffuser next to the door. Then the air goes to the whole room and is collected by the return. So there's something you have to do as good as possible. If the diffuser is more in the end, you will have much better movement of air, or with more elements, more diffusers, so you have more regularity, but you have to make sure the air gets well distributed through the room. Another very common system is the more divided area by individual ducts and then having plenty of diffusers in the whole room. Again, you need to design it in a way that the air is collected probably by a lower duct or some area or the ceiling. So the air is moving through the whole room. The ones on the right are less common, more modern. One which is integrated in the floor. So you have a expulsion and then collection to the ceiling, right? So you don't lose so much space. They're very nice because you integrate everything, you lose less space, but you have to calculate or plan very carefully so the service and the access to those areas is possible. And the last one is with a raised floor, right? So access floor or raised floor, in which you have the air coming from the bottom, which is good because if you have offices with individual places, you may have your individual air control. So you may have a much more variation between individuals. And you have to make sure the air is distributed regularly and collected in the same point. And of course, it can be, you can mix, right? So you could have the return going to the ceiling and so on, but okay, this is very common typology, most common in the left side, and less, but still possible on the right side. And this is an example of a ceiling part. This is a suspended ceiling, which tells you with the usual structures we use in Korea, we use big girders and then beam systems. We have a lack of available space. So at least you will need like half a meter to put your ducts, but the engineers will ask you for more than that. Engineers always want more. So if you use like a flat slabs or waffle slabs, you may reduce this to just 25 to 30 centimeters, and you're winning a lot of space for the other systems. Other possibilities to use castellated beams or available beams. You remember that are those beams which have openings, right? So you can pass systems through them. So if this beam has some opening, we could have this duct not so on the bottom, but much higher, and we are within the space. There are strategies, but the fact is that most engineers, especially here in Korea, use this kind of beam and girder system, and you're wasting something between 50 to almost 1 meter of space. And it is telling you that you need like 1.5 meters between structure, suspended ceiling, and in a building which has a 4 meters floor height, you will have barely 2.5 meters of usable space, even less, which is not a very efficient way to use a space. And in high rise, you accumulate through floors. So in a 10-floor building, you're maybe making a building which is 10 meters higher just because of this system than a building with the same number of floors, but with a more reasonable, more modern structural system. And this is why structure affects a lot, not only design, but also how those systems integrate in the building. And I think this is something to be considered seriously in the design. Make the difference of a building being 30 meters high or being 40 meters high to have the same inhabitable space. In terms of material, because you have a 25% more of facade. In terms of shade and sunshine you take away from the streets, in all aspects, it's kind of a waste. So I wish you consider that, and I wish engineers and architects also consider that. One thing you have to be careful always is that water is always under electricity. We try to put water in the lowest part, and if we have sewage, because sometimes we have a sewage pipe, sewage is underwater. Okay. This is not the case in the office, but usually have sewage, then water, and then electricity, and then the air. Air can be anywhere, always over the water, but since those ducts take a lot of space, since we need to access electricity or water for service, it's better those are under, right? So careful with this. So it's always air, electricity, water, and sewage if it is crossing somewhere by, right? So this is in the highest part, middle, lower. This is not so vital, only those two must be under, but since, as we said, air takes a lot of space, we put the first so we can always access and repair or service the lower elements. But I have a first question, because this is a very generic detail from the book, and after years, your Sombe designed their projects, and it seems that this detail is beautiful because they love it. And I bring some examples. So I go assignment to assignment, and I see this detail repeated over and over. So I can only think that either there's some kind of beauty I cannot find on it, or that there's no any intent to make any adaptation. I'm unfair, so some students try to put concrete structure and to make that more consistent with their project, but in most cases it's a literary copy, which I think is a pity because you're designing your building. So that diagram is telling you how much space you need and how you should layer those elements. And as I commented, the advantages and disadvantages of this kind of structural design. So when you go to your project, knowing that, you may make the detail which fits your case, right? Instead of just repeating what you say without maybe really understanding what you're copying. And if you understand it, why don't you process it and make your own detail? Well, that's a question I cannot understand. And just to end the lecture, MEP is usually hidden, but it's part of the design, it's part of the building. When we did our introductory lecture, especially in terms of the structures, we said the human body is also a very complex set of systems, which really fit a very integrated design concept, let's say. So we have the body And if we see the skeleton, we understand perfectly why the bones are like they are, and we understand it's a human being, or it's a dog, or it's a horse. But then we have the circulatory system, which is very much like the MEP, right, in terms of plumbing. And it's different than the skeleton, but still we can see the logic of it, and it fits the human body and so on. So I think the MEP is something which can be fitted into the design, even though we don't see it. If the design concept and the MEP network fit together, it's not only that it looks good, it is that the logic and the I don't know, the calculation, the design is much easier for those who calculate it, engineers, for those who build it, which is the construction company, and for those who maintain it, just the users and the maintenance companies. So I wish we also get that idea that a beautiful building has a beautiful MEP system, at least something which is consistent, not something you apply there without thinking, like forced from somebody else. So I brought some examples. This is Seagram Tower by Mies van der Rohe. What's the virtue of this building? Well, it has a side core, right? But you see the system is divided into parts, it's symmetrical, and it has a big effort on having most of the air coming through the facade. So it's kind of diffusers at a low speed, which regulate temperature in the most complex part. So it's where you have most of the heat or most of the cold in winter. So you have kind of air curtain, which then is collected through this kind of return ducts and taken in just two complexes, right? So this is okay. And of course, the diffusers are thought to be distributed more or less regularly in the ceiling without disturbing the design. Across the streets, we have the lever house, Gordon Bunshaft, maybe the best architect ever in SOM, in the golden age of SOM. This is a longer building, right, with a very also asymmetrical core. But again, you have maybe a more simplified system, but you have a set of impulsion systems into sides near the facade, and then a return system on the other side. So it's kind of symmetrical. As you know, that reduces the size of the shafts, and you can see how big they are, the main ducts. And you have very nicely distributed system, which is fitting mostly the working spaces. And you have less concentration where you have all this kind of closed rooms and the archives and elements which do not need so much air. So I don't think we need to say this is especially beautiful, but there is a logic which really works very well with the way that floor plan, that core, and that space planning is thought. More beautiful, Herman Hertzberger, Dutch architect, still alive, and Beher, or whatever this is read in Dutch. This is a very complex, very large office complex, which is modular, and it has a lot of well, individual connections. And you see that they have a large centralized room. This is a small factory, and a set of ducts that really fit very well this kind of modularity, right? And the logic of the units or the cluster of units themselves. So I think it's one of the most beautiful examples of very good coordination between architects and engineers. Maybe they don't have many more choices, but for sure, this is not improvised system. We can understand very well the space clusters, right? Being consistent with the branches of the different areas of the heating, and also having to do with the geographical position. So probably the independence or the regulations may be modularized depending on areas, not only on the design. And then another example, which is totally different philosophy. This is Norman Foster, IBM, large building, universal space, and they work by teams. So you have like small clusters of impulsion and return just by areas. And when you have the larger teams, you have a bit larger clusters. So this quite interesting design, which everything is diffused, kind of more democratic, more high technology. I don't know how to tell it. But in this large area, makes a lot of sense to decentralize those areas to have smaller farms and more independence in regulation by teams or areas. So maybe some part of the building is working and other is on holidays. Maybe some of them need hot and other need cold in other areas. So you have a lot of possibilities, even though the space is very much wide. And going to extremes, and this is quite near our days, we have this Googleplex messy building, but still again, there's no choice, but you have this kind of very arranged set of ducts, and then a bit more organic set of elements which fit the areas and the mood of the building. Or the minimalistic Bank of America, which uses that system we said of under the ground conditioning. So each working place has its own individual control, which is great because the theory behind that is that you use only what you need to reach your level of comfort. So it should be most efficient and most energy effective system. However, reports seem to say that for some reason this kind of system spends more energy. So maybe it is not a problem of design, but maybe problem of use. We don't know what, but maybe things change with time. But interesting experiment. But what we want to say here is that you see that MEP, and this is the hidden part, then we have the diffusers, which you see, but that system works better when fitting the design concept. And I think in that part, architects, owner, engineers need to agree on what is better, what fits better the way the building is used. As an example, this is Katy Tower, the example we bring very often. This light changes, and you see in a very well-planned tower how much space is taken by the ducts. See how many beams have openings to have ducts in, and as we said, you have the air on the top in general, then electricity, and then pipes just in the lower part. This is the most general way of doing things. But you see that there is a connection. So here the space is so tight that mechanical, plumbing, and the structural engineers have to really check and cross-check the working drawings so there will not be any disaster. Then you see also the openings in beams. So at some point you have no choice. And of course you cannot improvise this. This should be calculated before the building is made. And well, you see sometimes the fireproofing is broken and that should be repaired afterwards. And this is the diffusers to have a very, as we saw with MES, a very continuous and diffuse air in the most difficult part of the building, which is the glass in the facade. So you have a diffuse, but with a low speed. That means having more diffusers, but they have less feeling of that uncomfortable hot or warmer. So you don't feel almost the air moving, but you have a lot of volume, right? So it's large volume, but a low speed. So you have a very good regulation of the air without having uncomfort. And this is how it looks when it's finished. So you have diffusers which actually take more than 50% of the area, and there is starting there and disconnected in the other side of the floor. And finally, this is the two last slides. I have some tables taken from the reference material. This is, you have an example. I put it here to let you know that you have a table to calculate a rough estimation of that cooling equipment, and you have square meters or megacalories and well, square meters for areas, not only square foot, and also for the air handling units. And with these two tables, you may pretty mention all the spaces you need. This is for large buildings, but large buildings starting on 500 square meters. It's not so large buildings. So in almost all your buildings, you may have a rough estimation on how much space you need for those rooms, and you will be able to control it. The details are in the reference materials in the Blackboard. Also, you have a basic explanation here, and it's not very hard to see how they are arranged. So you have curves depending on the kind of typologies. You start with the size, and they will have, depending on the typology, different areas for how much volume you need, how much is the size of the return and impulsion ducts. And one annotation here, they calculated roughly. So it's more complex than that, but we're speaking of three-dimensioning. Let engineers do the hard work, but let us just prepare the building so we don't need to have big changes. But it's calculated by air speed of about 10 meters per second, which is quite standard, but it's quite high. So it's kind of noisy, but this reduces the set of pipes. So you will have this in garages, in shopping centers, in areas like that. But high quality offices, not innovation building in campus, but high quality offices like a KT Tower or theaters, maybe not a bang are noisy, so they don't need that. You will, or maybe hospitals, especially in the patient areas and places where you need concentration, you will try to reduce under 4 meters per second or even less. You cannot reduce too much because then you will have other problems, right? But you'll have a huge ducts, but 3-4 meters per second reduce noise, reduce also the stat circulation, reduce the wind, and have much more comfortable feeling. But that means you will have to increase the pipes in the same proportion. So with these two tables, we finish, we complete the set of lectures, well, the first part of the MEP, and the following lecture will deal with the remaining plumbing and conveyance and safety. As usual, if you have any comment or problem or question, you can always email or put your comments in the YouTube channel. That said, if you liked it, remember to like and subscribe, and see you in the next lecture. Goodbye.